All right, morning. Welcome to Monday. Yeah, seem pretty sleepy. Okay, pretty exciting weekend. And so this week we're going to be doing in the lab, we're going to do vibrational spectroscopy. So you're going to be doing Raman and IR. And so you'll get to see the Raman instrument that we have upstairs. You can do the sample analysis and so on if you want. You can sit and watch. You can also look at the Raman Spectrometer. We have a 532 nanometer laser. It's a new system. When I first got here, we bought a 785 nanometer system because it fluoresces less, and we'll talk a little bit about that this morning. But I realized most of my work is done with solvents, and solvents don't fluoresce that much. And so I was able to use a 532. After the flood that we had here 2 years ago, the instrument was completely destroyed. So we got a new one. So we have all new equipment, and so that's nice. So this morning we're going to focus on the theory and the equipment for the Raman spectroscopy. And so for the electromagnetic spectrum, in this area we're using visible light. Oh, I think we flipped over to that. Let's see. Let's try source here. Let me do this. Yay. Okay, thank you. All right. I had to wake it up. Okay, so we're using visible light to measure vibrational properties in the mid-infrared. So if you think about that, we'll just have a slide on this where we're showing the visible spectrum and what the difference in those photons are. They show up in the mid-infrared region. The types of spectrometers, you know, we had last time two types. We had dispersive spectrometers and we had interferometric spectrometers that use some sort of either frequency difference or mirror displacement in an interferometer. Well, most of your Raman spectrometers are dispersive. And then the types of transitions, we're looking for the Raman effect, which is inelastic scattering. But what we have also is absorption that can occur. And so if you have a colored sample and you're using a visible laser, that's probably a bad combination because colored samples absorb visible light. If you're hitting it with a visible laser and you absorb that laser energy, you're putting a lot of energy into the sample and you can catch it on fire. So in order to avoid that, you want to move the sample quickly or move the laser quickly. So you can have automatic mirror systems that raster the laser over a large area of surface. And so that's a way to keep any particular spot of the sample from heating up. Or you can put the sample, if it's a powder, you put it in a little ring. So if you think of a disc, that you cut a groove in that disc, you can sort of putty your sample into that groove and spin that disc and shine the laser on that ring of sample. And so your sample's flying by the laser very quickly. The Raman effect takes place very fast, 10 to the minus 15 to 10 to the minus 12 seconds. And so it's happening before that sample moves out of the way. So you can spin the sample to keep it from heating up. And then fluorescence is really the number one enemy of Raman spectroscopy. So even if your laser line doesn't hit a strong absorbance, it may still be absorbed. Some of it may still be absorbed by the sample, and then it may fluoresce. And so that fluorescent signal is going to be red shifted. When we get to electronic spectroscopy, you'll understand how the fluorescence works. So that red shifted light is very broad in its emission, and the Raman spectrum is very narrow. So the Raman transitions are very narrow peaks corresponding to the vibrational spectrum of the molecule. But fluorescence is an electronic spectrum. And electronic spectra are very broad. So you get all of this smear of light, and on top of that is your tiny little Raman signal. So it just overwhelms the detector, and you don't get to see the Raman. So fluorescence is the enemy of Raman spectroscopy. That's something that you can write down as sort of a rule of thumb. If you're always having this competition between the Raman signal and fluorescence. It won't be a problem for our samples, again, because we're using solvents and small molecules, and the fluorescence signal for benzene and chlorobenzene is really small, so we won't have a problem with fluorescence. Here's a picture that we had last time of the electromagnetic spectrum. And so in pictorial form, what I just told you is what's shown here. We have the visible spectrum here, and we have a 532 nanometer laser, and our mid-infrared spectrum is going to be spread out between 400 up here and 4,000 wave numbers. So that's going to have the whole vibrational spectrum of our molecule. And so that's the difference between the incoming light and the outgoing light. And so take a 3,000 wave number stretch. One of the largest differences would be 3,000 wave numbers. And that is, if you have an incident light of 532 nanometers here, then the Stokes shifted light from a 3,000 wave number stretch would be 633 nanometers. So our whole spectrum is coming out in shifted visible photons. So we send in 532 nanometer light, and out comes all these other colors. And if we were to disperse those colors and send them onto a detector, we would get the visible spectrum. You'd see all these peaks that correspond to the Raman effect. If we plot the difference between 532 and all of those peaks, then we get the vibrational spectrum that we can line up with the FTIR. So what we're plotting this week in lab is actually Raman shift. So it's the wavelengths that we detected minus the incident wavelengths. And so that difference is the vibrational differences. We'll see that in an energy level diagram here in a second. Now this is the Raman effect, not the Raman effect. Okay, so it's not the noodles, it's the scientists, the Indian scientist who won the Nobel Prize for this effect in 1930. He used sunlight and was looking into a box. He had a blue filter letting blue light into the box. He had a sample. He had a red filter on outgoing light. So none of the blue light could come out and hit his eye. Once his eye adjusted, he could see light in the box. So he could see this Raman scattering from the samples, and he published that work. This is a modern day Raman setup. That's me in grad school. Okay, and I'm pointing to the output of our laser. We also had a Neodymium Yag laser. Now the one we have in the lab is at 532 nanometers, which is actually the principal emission line from a Neodymium Yag laser that's been doubled in frequency, or the wavelength's been cut in half. So 1064 is the infrared light that comes out of a neodymium crystal, and that's the laser that we use, and then we double that frequency with a frequency doubling crystal, and then that gives us half the wavelength, or 532 nanometer light that comes out. So we had also a pulsed system. So what I'm standing next to over here, this is the power supply, and it's about the size of a washing machine, and it's water cooled, and the energy would come up this umbilical cord here and go in here, and all that energy would be in these flash lamps, these clear discharge tubes, and it would pump all of this energy into these flash lamps, and then that would put visible light into this Neodymium Yag crystal. So what's the Neodymium Yag stand for? Well, neodymium is the element that they've doped the yttrium aluminum garnet crystal with. And so we're getting the emission spectrum of the neodymium atom, which has a laser line at 1064 nanometers. We would pulse that light and get out 10 pulses per second, and the pulses would be 10 nanoseconds in width. So all of that energy was coming out in 10 nanosecond chunks. So if you take the energy, which was a few millijoules, and stick that in 10 nanoseconds, then you've got joules per second, you've got watts, and that was megawatts of power. So the molecules felt 10 megawatts of power. Now to give you an idea of megawatts, well, Roan's Prairie, that power plant that we drive by on the way to College Station, is 500 megawatts. So that's only 50 times more than what this laser was putting onto a molecule. So anyway, it's pretty amazing. After 50 pulses, we've put 500 megawatts into a molecule, or several molecules. And so what does that do for us? Well, it really shakes the electron cloud and gives a higher probability of the Raman scattering effect. So that's what we were doing with our spectroscopy. Now we've miniaturized things. With diode lasers, we don't need water cooling. We can use air cooling. And so in these instruments, you've got a power supply, you've got the laser, and you've got the spectrometer. This is a fiber optic cable that comes out, a little safety mirror to keep the laser from coming out when you don't want it to, and then you have this little sample chamber. The nice thing about these sample chambers is all the laser lights contained, so you don't need to wear goggles. And so we can come into the lab, we can set up our samples, and we can use this sample holder, and all the laser lights contained in this little dark block. This is a handheld one where the spectrometer and the power supply are all inside this little handheld system. It's just got 3 buttons. So this would be a field instrument. You could go, and if you had a library of compounds programmed in, let's say you had all the illicit drugs in here, and you could look at a powder and it could tell you what that drug was. If it wasn't in the library, then you should have some sort of quality check that says unknown, so it doesn't just pick the one that's closest to. And so you would, in that case, be getting a lot of false positives. And so this is a pretty easy field technique now. These things can be battery powered. Let's review a little bit. This is Raman spectroscopy, and it's using the Raman effect, which is inelastic scattering. We have elastic scattering, which is the Rayleigh scattering. So if the laser line comes in at 532 nanometer light, which is a green photon, and it comes out without any change in energy, that's elastic scattering. How do we know if scattering happens? Well, it comes off at a different angle. If it stays in the same path, then it's just transmission. So the 532 nanometer light may hit a molecule, it may be emitted or bounce off, it goes straight through, that's just transmission. And the speed at which that happens, it would be the speed of light in that medium. And the ratio of the speed of light in the medium versus the speed of light in a vacuum is the refractive index. So you've heard of refractive index, that's just how that light slows down in a particular medium. But if it comes off at a different angle, that's scattering. If there's been no energy change, it's elastic scattering. If there has been an energy change, it's inelastic scattering. If you take that inelastic scattering signal and you see in particular peaks, you're seeing that Raman effect. It happens based upon this beat pattern that's set up between the different frequencies. You have 3 frequencies involved. You have the frequency of the incident light, you have the frequency of the vibration of the molecule, and you have the frequency of the photon that leaves. And so if you've ever played an instrument, let's say you're trying to tune a trumpet or a flute, you've got the tone for the tuner, and you get close to that tone, but you're off a little bit, you'll hear a 3rd frequency. It'll have a beat pattern. It'll get loud and soft, loud and soft, loud and soft. Well, that loud and soft beat pattern is much lower frequency than the original 2 tones, the tone from the tuner and the tone you're playing. And that difference is, in the Raman effect, the vibrational difference. And so it's that detuned tone, that beat pattern, that happens if it matches one of the vibrations in the molecule, then that shorter tone can be scattered off. And so then that photon is generated by this interaction. Now we have 2 types of inelastic scattering. If we're in the ground state, it's more probable that we'll have Stokes scattering. So it will be the one on the left here. The laser light will come in. So your frequency comes in, and then it oscillates with the molecule. And if that beat pattern is established and it spits out an elastically scattered photon, then that one comes out. An inelastically scattered photon. And so if the photon is redshifted, a longer wavelength or shorter energy, then that's called Stokes scattering. If you have molecules in a hot band or hot level here, the green light can come in and hit that excited molecule and cause it to relax. And so then you can have a blue shifted photon. So these colors aren't just for grins, they actually are showing the red shift and the blue shifted laser lines. And so let's do some math, let's practice. So if the laser line is 532 nanometers, What is the Stokes wavelength of light scattered by the CH stretch? So we know the wavelength of the laser, 532 nanometers. This would be very similar to the type of an exam question in the second portions of the exam. And I'm going to try to do more of these in class because people have requested that to kind of show some of the thinking through some of these problems. So we're dealing with wavelength, but this elastic scattering happens in energy, right? So we're talking about energy coming in and energy coming out. And so energy is proportional to wave number, not wavelength. So let's do everything in wave numbers. Whenever we're calculating these differences, do the differences in wave number, not wavelength. Okay? And so we want to get out of wavelength. So 532 nanometers. And so we have nanometers and we want to get to wave numbers. So always begin with the end in mind. You want the end result to be Cm to the minus 1. And so just using straightforward dimensional analysis, you're looking at this and you're saying, okay, I'm going to get out of nanometers and get into wave numbers. Get into centimeters. And so let's just use our knowledge of the metric system. Nano is what? 10 to the minus 9. And centi is 10 to the minus 2. So centi and nano work there. And so what we end up with, if we simplify all of this, is a 10 to the 7 on bottom. And now one problem, though, is we end up with wave numbers here, okay? And, we on the right, but we have centimeters on the left. And we cannot make that mistake. A lot of people made that on the exam. They just completely ignored the minus 1 on the wave numbers. And so how can we fix that? We've got our dimensional analysis worked out, but it's not going to equal the thing on the right unless we raise this whole thing, unless we raise this whole thing to a minus 1. So do the calculation and then invert it. And that was the one step that threw people off about 4 orders of magnitude. Now, many of you were able to get to the end and say, well, I got the 1.67 right on the mass of the proton, but you were off by 2. Some people were off 2 and others were off 4 orders of magnitude because they didn't invert what they had calculated. Okay. And so essentially we have 10 to the 7 divided by 532. What'd you end up with? You deleted it? Okay. Someone else. $18,700. Okay. So we end up with 18,000. Let's go with 797. Let's think about that. The infrared region was 400 to 4,000 wave numbers, and this is in the visible. So that makes sense. It should be a lot higher. Okay. So we're in the 18,000 wave number range for a visible photon. Now, that's the incoming light. 532 nanometers is 18,000 wave numbers. And then it hits the molecule, a CH stretch occurs and steals 3,000 of those wave numbers. So what comes out is something less, 3,000 wave numbers less. So we can take that, we could subtract 3,000 wave numbers for the CH stretch. And so this is the inelastic scattering. It's lost 3,000 wave numbers, and it comes out at 15,000. So let's convert that back because we want to know what the Stokes wavelength is. What wavelength of light is that going to be? If we looked at a visible spectrum, where would that peak be in the visible spectrum? You're going to like this 10 to the 7 thing, okay? So it's always 10 to the 7 nanometers per centimeter. And if I just take that 10 to the 7 and divide by my frequency and wave numbers, I get to nanometers. If I take that 10 to the 7 and divide by nanometers, I get wave numbers. And so 10 to the 7 is very nice. It's that conversion of nanometers to centimeters. And you're always dividing either the wavelength or dividing the wave number, and you can convert from one to the other. Do you see how the units work out? I have 1 over wave number, 1 over centimeter on the top, 1 over centimeter on the bottom. So those cancel, and I end up with nanometers. I think that's 633. So I hit the sample with a 532 nanometer laser, and if I have a filter there, I don't see it, but I see a bright peak at 633 nanometers. And that difference is there because of the CH stretch. Now, if I don't have CH bonds in my molecule, I won't see that peak. But if I do have CH bonds in the molecule, then I might see that peak. It's about 1 in a billion chance. Okay, so I have 1 billion times more photons on my laser that are Rayleigh scattered. And so out of every billion Rayleigh scattered photons, I'll have 1 photon of this Raman scattered light. Doesn't sound very great, but there's quadrillions and billions of photons in that laser. And so then we have enough signal that we can see in our detector for the Raman effect. Let's twist it a little bit now. If the incident laser line is 532 nanometers, what's the anti-Stokes wavelength of light for a CH stretch? So you got to know what Stokes and anti-Stokes is. So let's draw an energy level diagram just to make sure we have it straightforward. Actually, let's dash that. So we have a dashed line up here. It's registering double click. So the light comes in, interacts with the molecule, and comes down to a further down level. So that's the anti-Stokes situation. And so this difference here, we calculated as 532 nanometers, which was 18,787 wave numbers. And this difference was 3,000. So do you see why the energy level diagrams are useful? You can just look at them in terms of energy and add them or subtract them. And so we're taking the 18,000 and adding 3 more thousand wave numbers. And so we end up with 18, 19, 20, 21,787. So that's the resulting energy of the anti-Stokes scattered photon. 780 or 797, which was it? 797?
797.
Yeah. Okay. So we can take 10 to the 7 nanometers per centimeter and divide by 21,797. What'd you end up with?
459.
459, okay. Nanometers. You're only going to see this in excited molecules, thermally excited molecules. So you would have to have a molecule with a CH bond, essentially a CH stretch in the excited vibrational state. It's not very likely, okay? But you might see this in combustion reactions or some kind of plasma, some kind of really high temperature situation. So a CH stretch would be very difficult to get an anti-Stokes transition out of. But if you were able to get one, that photon would show up at 459 nanometers in the visible spectrum if you were using a 532 laser. The nice thing about anti-Stokes spectroscopy is that fluorescence is always redshifted. And remember I said fluorescence is the enemy of the Raman effect in terms of the signal, right? So if you can get anti-Stokes spectroscopy, then you don't have to deal with fluorescence. So it's a zero background. You're not going to get blue shifted fluorescence. You're only going to get red shifted fluorescence. If you can get blue shifted Raman, then you don't see the fluorescence. And they call it a zero background technique. There's nothing else that's going to happen in the blue side of a 532 nanometer laser. Nothing else is going to happen on the blue side than anti-Stokes Raman. So if you can see those peaks on the blue side, then you know you're seeing anti-Stokes Raman peaks. Let's look now at some of the symmetries of these different transitions. So we have the incident light. You don't have an actual energy level. That's called a virtual state. And you have the inelastically scattered light. And you have one of these for every vibration in the molecule. Now, they may or may not be Raman active, but you still have that vibrational potential. And only the Raman active peaks are going to have the Raman effect. So how do we determine Raman activity? We use all of the double combinations of the Cartesian symmetries. So x squared, y squared, z squared would be similar to the photons coming out and going in with the polarization that's preserved. So x polarization coming in and x polarization coming out. That would be an x squared symmetry. Something that rotated the polarization of light, and that can happen. Let's say you have a motion that's along x and y, and so light comes in interacting on the z-axis, and that motion causes the polarization of light to be rotated and come off on the x or the y. So you might have a zy or a zx Raman effect. And so it would rotate the polarization of light, and you can detect those modes by having a polarizer on your incident laser. So the 532 nanometer light comes in polarized one way, and then on the detector you can have that polarized filter turn 90 degrees. And so you could only detect those modes of the molecule that rotate the plane of polarization. And that simplifies the spectrum as well. You could also keep the polarizers vertical and only see those modes there where the polarization of light is preserved. And so there's this depolarization ratio that you can use in the Raman effect, and we can actually see that in the Gaussian calculations. So when you look at the Gaussian output, you have the vibrational frequency, you have the number, the vibrational mode number, you have the symmetry, then you have the vibrational frequency, then you have the infrared intensity, and the Raman activity. So when you're plotting your spectra this week in lab, the infrared intensity would be what you use to plot the infrared spectrum. And the Raman activity is what you use to plot the Raman spectrum. But there's also a thing called the depolarization ratio. You're going to ignore that for this week's lab, but that's what you would use if you wanted to model this cross-polarized experiment. And so you could go in and see what the spectrum would look like with cross-polarizers or with uncrossed polarizers, with vertical polarizers. And then now we have sort of this idea where you have every one of these different vibrational modes having its own peak. So down here you have the ground state. If the incident line returns to that ground state, you have Rayleigh scattering. Here you have excitation in mode 1. Here you have excitation in mode 2. Here you have excitation in vibrational mode 3 and vibrational mode 4, and it goes on and on and on. And this would be the Gaussian numbering. It's going to start at the bottom with the lowest frequency mode and just number them from the bottom up. In this week's lab, I talk a lot about Hertzberg. Gerhard Hertzberg in the early 1900s was one of the scientists who analyzed small molecular spectra. This was the days when they used photographic film. And so instead of a detector, they would have a dispersing element like a grating, and they would just expose film. And you would see dark lines of exposed light wherever these Raman peaks showed up. And so that's where they got called lines, because they were lines on a photographic plate. And so then he would analyze those, and then he also cataloged all of the different vibrational experiments in his book, the Vibrational Spectra of Diatomic Molecules. He wrote one on polyatomic molecules and so on. And he came up with the numbering scheme. So that experiment where you had the polarizers in a vertical position for the incident and exiting light, those would be the symmetric modes, and he would start at the high frequency and label that vibration number 1 or nu 1, and then he would go down to the next highest frequency fully symmetric mode, and he would label that nu 2, and then he would go back and switch the polarizers and then label the peaks for the asymmetric modes from the high frequency to the low frequency. So that's how the numbering scheme for Hertzberg works. But it got confusing because as we got to more asymmetric molecules, you had no symmetric modes and so on. So we just decided to scrap that and go with the Gaussian, where you number them from low to high, 1 through 3n - 6. So we have two different numbering schemes. Now science is actually has a very big problem with inconsistency. And so we don't want to have Hertzberg number these vibrational modes in the 1900s and then all of a sudden start switching our numbering. We want to keep Hertzberg's numbering scheme for the molecules that are in his book. So that when I talk about nu 2 for CO2, I'm using the same nu 2 that they used in the early 1900s. If I start using Gaussian's numbering, then nu 2 doesn't have the same meaning. Its meaning changed over time. And so we don't want that. So in your lab, you'll see the vibrational assignment for benzene, which is in Hertzberg's book. And it has a very confusing numbering scheme. But if you take what I said this morning and look at it, you'll see for the symmetric modes, nu 1 is the highest frequency symmetric mode. Nu 2 is down in the middle somewhere. And then you see the asymmetric modes. Now a high frequency is nu 3, nu 4, nu 5, and it works its way down. So you can see this scheme in Hertzberg. But then when we get to chlorobenzene, the one that you're analyzing, just use the Gaussian numbering scheme, because chlorobenzene is not in Hertzberg's book. In fact, I've looked on NIST, I've looked on SciFinder Scholar, I haven't found a vibrational mode assignment for chlorobenzene. So if you were really meticulous and you got in there and you assigned all 30 vibrational modes to a spectroscopic signature and you're able to support your assignment, you could publish that with the data that you get in this lab. Okay. It's a pretty tough job though, because there are 30 vibrational modes that are allowed in the Raman and the IR. And so you'll see how busy the spectrum is. I'm just asking you to assign 12. Okay. So that kind of gives you a hint as to how hard it is. I'm just asking you to do 12 out of the 30. Okay, but you'll do the 12 biggest peaks. So I picked the easiest ones, but even then it's a little tricky, because if you just go by frequency, Gaussian will give you some of the, the ordering of these peaks, but some of them are jammed pretty close to each other. So you're going to also want to use the intensity that Gaussian predicts, because you'll have a big peak in the spectrum, and the one, if you sort them in order, that might be a really short peak in the Gaussian output, but right next to it is a Gaussian peak with a really big intensity. So it's probably not just sorted high to low the right assignment. You might have to look at the intensity and say, well, even though this peak is coming out at a little bit lower frequency, it's got the intensity that would match this strong peak in the spectrum. And so you need to defend your assignment. And it's not too hard. You just look at the frequencies. That gets you 90% of the way there. And then look at the intensities and line those up for something in the same region. Okay. And so that's what your defense would be. If you're saying, I'm assigning this peak to 1537 wave numbers because it's close, and it has the right intensity to match what I see in the visible spectrum, or what I see in the Raman spectrum. And then the one that is closer in frequency doesn't match in terms of intensity. So that's the kind of explanation that I would be looking for. And then when we, another skill that we're going to learn this week is how to stack plots. And so you've done well in learning how to plot your wave functions and so on. But this week we're going to have 4 spectra that are simulated. So we'll have the Gaussian simulation of the Raman and the IR for both chlorobenzene and for benzene. Now it would be nice to have all 4 of those on the same plot. But if they're all at 0, starting at 0, their peaks are going to be overlapped. And it's going to be very difficult to see the spectra. So also, the Raman spectrum, maximum y-axis point is around 10,000, sometimes 15,000 counts. So that's the number of photons that are hitting our detector. And the infrared spectrum is in attenuated reflectance. It's kind of like absorbance. And that's going to be like 0.5, maybe 0.7. And so if you plot 0.7 peak on the same scale as 10,000, your 0.7 is going to be undetectable. And so we want to use normalized intensity. And so in the lab, look at that formula where you take your 0.7 and you divide it by the maximum peak in that spectrum. Let's say 0.7 was the maximum. Now it has a range of 0 to 1 for your absorbance spectrum. And then if 10,000 was your maximum peak in the Raman and you divide that whole spectrum by 10,000, now it goes from 0 to 1. And we can plot those on the same y-axis and call it relative intensity. And so then all your spectra go from 0 to 1. Still, though, if they're on top of each other, that's difficult to see. And so we're just going to add a constant to those. And so you can add a constant to the whole spectrum and just shift it up a little bit. And you can put all 4 on the same plot, stacked by these constants. And so every spectrum will be normalized, 0 to 1, and stacked, maybe 0.5 to 1.5, or 1 to 2, or 1.5 to 2.5. And so when you plot all 4 of those on top of each other, then you can see this is the Raman spectrum for chlorobenzene and the Raman spectrum for benzene. And here's the IR spectrum for both. And so we'll have simulated and we'll have experimental spectra. We've got 8 spectra, okay? So we have the experimental Raman and IR, and we have the simulated Raman and IR for 2 molecules. And so we're going to do a stacked spectrum of all simulated and a stacked spectrum of all experimental. And then we want to see how well the simulation for benzene matches the experiment. So we'll have the simulated for benzene and the experimental for benzene. And so that's another 4 spectra. And then we have the simulated for chlorobenzene and the simulated and the experimental for chlorobenzene. So you're going to have 4 stacked plots. That's 16 spectra. And once you learn the first one, then the next 3 are pretty easy. Okay. So that's what I've done. I've also had some mercy on you. I did the first 3 simulated ones just to show you how to do it. You do the 4th, okay? And that reduces the tedium quite a bit. Instead of typing in 30 peaks for chlorobenzene in the infrared and 30 peaks for the Raman, I did that for you. I'm asking you to do the 5 or 6 that are active for benzene. So that'll get you the idea of how it's done, taking output from Gaussian and putting it into Excel. And as far as simulating the Excel spectrum, you've already simulated spectra. You did the particle in a box. And so remember, every one of those peaks had a delta E and a wavelength and a transition dipole moment calculation, intensity, and the Boltzmann factor. And every peak was simulated, and then you summed them across. Now we can take all that particle in the box stuff and delete it and just type in the Gaussian wavelengths and the Gaussian intensities. And then that same spreadsheet works for simulating Gaussian spectra. Okay, so we can simulate the Raman spectra that way and the IR spectra. So I've cleaned that spreadsheet up and put it on Blackboard so you can just download it, and you'll see it will look familiar, but it'll be slightly different. But it'll look familiar in general terms to what you did for a particle in a box. So that's why I was kind of out of my office last week. I was preparing the new and improved lab section handout for this week's lab and then making that spreadsheet for you. All right, so let's look one more time at the instrument. So this is essentially how the instrument's constructed. The Yag laser comes in, hits the sample. Most of what's happening is Rayleigh scattering. So that green light is coming off the sample and going everywhere. And there's a small amount of the Raman light, the inelastic scattering. Most of the light is wasted, goes into a beam dump, if you will, trash can. And then we use that visible spectrometer, the USB spectrometer, that has a grating in it and a diode array, and then some electronics to turn it into a data point file. So all we do is we'll put in our sample, close the lid, and wait till the spectrum stabilizes, and then we'll save that spectrum to a text file. And then we'll bring that text file into Excel and paste it in. And then you'll use the text to columns tool under the data ribbon to make sure you have the X and Y values in 2 different columns. And then you're ready to go. We got some time for questions. Anything on the homework, anything on today, reactions to this week's lab. Hopefully the board work helped in doing some of those calculations. There'll be similar types of questions. The main thing about the questions is not so much the calculation, it's understanding what the question is saying. Right? You read those words, and it's as much a vocabulary question as it is a calculation question. If you don't understand the words that are in the problem, then you're really sunk in terms of doing the math. All right, I'll see you next time.